Okay, so our next presentation is Understanding the Implementation and Security Implications of Protective DNS Services. And Yiming Zhang from Tsinghua University is going to be presenting. Take it away.
Okay, thanks for the introduction. Hi, everyone. I'm Yiming Zhang from Tsinghua University to show our work, Understanding the Implementation and Security Implications of Protective DNS Services. It is a joint work with DJC Lab and the Qianxin Institute. Okay, I will start the talk by introducing what is protective DNS service. Sending DNS queries to the resolver to translate one domain name to its IP address is often the start of internet services, but domain names have widely been abused by attackers for cyber attacks like malware, Trojan, and botnet. So blocking the resolution process of malicious domains could be an effective way to fight against cyber attacks. To this end, the security community has proposed a new mechanism called protective DNS. I will use an example to show how it works. If you use a normal DNS resolver to visit a phishing domain, the resolver will do the regular recursive resolution process and finally return you an IP address with malicious content. Then you might be phished. But if you change to use a protective DNS service, the resolver would first check if the domain you are querying hid in its threat intelligence a blacklist of malicious domain. And if it finds you are visiting a phishing domain, it will just rewrite the responses to return some secure responses to you. For example, an IP address that held by the resolver itself with an informational page to indicate while you are visiting a phishing domain, and we have helped you to block it. Considering its benefits, although have not been proposed for long, the PDNS have gained support from dozens of large DNS services like Cloudflare and Code9. And countries like the US and Canada have also released initiatives to establish national PDNS infrastructure. But up to now, little has been known about the current deployment status and working mechanisms of PDNS services. So this work fills this research gap by providing the first large-scale measurement towards real-world PDNS services. And we answer a series of research questions, including how many DNS servers in the world are offering PDNS services, and what are the blocking policies, which may be vary from different providers. And although PDNS was designed to enhance security, but if they were deployed in problematic ways, they will introduce new security risks, and we want to find them. Our work can be convoluted into three parts. First, we propose a methodology to filter out PDNS out of OpenDNS resolvers, and we identified a total of 17,000 PDNS servers in the world. And we try to understand the working mechanisms of PDNS ecosystem. We gave the first large-scale active measurement study of the identified PDNS services and to review the block lists and the rewriting policies. Then we did a security analysis of the current PDNS services and found 3 types of new security risks due to their flawed implementations. I will first introduce our methodology. Up to now, there has been no public standards for PDNS. So we first investigated the most top DNS vendors with the most market share, about 42 vendors, and found 28 of them have publicly claimed that they have deployed PDNS services. So we use these public DNS vendors as an empirical study. We know that PDNS has 2 important components. The first is its domain block list. Based on the empirical study, we found those 28 public PDNS services could both use open source domain block lists and their self-built private domain block lists. And the second is their rewriting policies. That is, how would they respond to users' queries towards malicious domains? And to know that, we built a small site of malicious domain lists, sending their requests to those 28 public DNS servers and see their responses. And based on the responses, we can classify their rewriting policies into 5 types, including a special use IP address, like the reserved IP address 0000, and secure IP addresses and synonyms that held by the providers themselves, or they would change the response code of the DNS queries, DNS responses to some error codes, or just exclude any answers from the responses. So we propose a 3-type identification method for PDNS, and the core idea is to check whether the resolver would rewrite the responses of malicious domains. So the first time is to build a domain list for testing. We first select 1,000 malicious domains from 7 public block lists covering 3 malicious categories. And to check whether the DNS service is still available, we also include 100 popular domains from the Trunco top list as the reference. Then the second step is to query the domain list towards open DNS resolvers globally. And to know whether the answer has been rewritten, we also need to know what are the correct answer, what are the unmodified answer. So in this work, we use the responses from the authoritative servers of those domains and from a passive DNS data site as the reference. After distinguishing the modifications, we also need to further distinguish whether the modifications are from PDNS or from other types of DNS manipulations. For example, the man-in-the-middle DNS hijacking or the censorship. So we built a series of filters for that. For example, to distinguish censorship, we referred to existing methods to actively measure the censorship. And to identify the censored domains, and we excluded them from our data site. And other manipulations were excluded via similar rule-based algorithms. And for time reasons, you can check the details in our paper. We use vantage points located in 3 countries to actively probe the PDNS resolvers in the world. And to mitigate the impact of network jitters, we repeated the scanning experiments for 6 times and only reserved the intersected results as the stable PDNS resolvers. And we found a total of 17,000 of such resolvers have been deployed around the world, covering over 100 countries and over 1,000 of AS. And here we list the top 10 countries and ASNs with the most PDNS resolvers found. We can see that the US dominates the most PDNS resolvers. It has been mentioned that the US has published its official PDNS policies to establish national PDNS infrastructure, which may have facilitated its deployment. We also use a representative metric, the round-trip time, the RTT, to evaluate the querying performance of PDNS. Here, the RTT refers to the time span between we send DNS queries to and get DNS responses from the resolver. And as the performance may vary for both blocked or unblocked domains with or without DNS cache, we did 4 different experiments under different settings, and we found when without cache, PDNS could respond quicker to blocked domains than other domains. If we use cache, the difference becomes less pronounced. We speculated that the reason of such performance is PDNS prefers to block domains before the recursive resolution. So the disable of DNS cache would not impact the RTT of block domains. We also checked the block lists used by PDNS vendors and found 57% of PDNS vendors could block over 500 malicious domains. But we also checked the most top PDNS vendors with a wider range of user base and found they take a more conservative choice of block list. 43% of them block only fewer than 100 domains. And the further investigation showed that they only concerned on high-risk domains like the domains from malware or botnet. And we think such conservative choice may be driven by usability concerns as the top PDNS may have a more complex and larger user base. So aggressively blocking domain names may trigger large amount of user complaints to impact their business. We also check the similarity used by block lists between different DNS providers and found some of them exhibit significant correlations. For example, Code9, in addition to being a PDNS provider, is also a public threat intelligence provider. And we found several PDNS vendors like the Ali DNS and the DNS Pod may directly use Code9's block lists, as their similarity are all over 80%. And we found that the Sky DNS and the Safe DNS are almost the parallel services, as they use almost the same block list for PDNS services. And we also found some outliers like the alternate DNS who use a separate list. As for their rewriting policies, we found secure IP is the most prevalent policy, adopted by over 56% of PDNS providers, and we found 28% of the IPs have been configured with an informational web page to make the user be aware of the blocking, and 14 IPs also provide avenues for user complaints. We also found PDNS providers would use different rewriting policies towards different malicious domains. For example, one resolver could use the reserved IP address 0000 to block malware and Bonai domains, while use the self-controlled secure IP 1.1234 to block other types of malicious domains. And we also found that the PDNS resolvers who have the same rewriting policies especially use the same secure IPs, as the IPs are controlled by the vendors themselves, maybe belong to the same DNS vendors. So we group the identified DNS resolvers into groups and found 12 large groups having over 50 DNS servers. We also did a security analysis of the PDNS infrastructure and found 3 security threats. The first threat is the denial of response threat. We found 800 of PDNS employ no data to block malicious domains, but 28 of them are too aggressive, which means if they find a client continuously acquiring malicious domains, it will block all the following queries from this client. So an attacker could spoof the victim's IP address and sending multiple malicious queries to the resolver, then the victim's DNS service would be interrupted. Our experiment showed that even 7 popular PDNS providers with large user bases are vulnerable to this threat, and the interruption could last up to 12 hours. And the second threat is the dangling PDNS infrastructure. It has been mentioned before that PDNS could use a secure IP as the rewritten answer, and the secure IP is the most dominant policy. But we found some of the IPs are dangling IPs, which can be taken over by attackers. Those IPs could have been allocated from cloud services, but have been expired, so the attacker could use the same cloud services to apply for those IP addresses and then take over the resolution results of those domains. And we found 7 such IP addresses are dangling, employed by 21 PDNS vendors, and could impact hundreds of domains resolutions. We also see subversions of protective features of PDNS. The first is we found over 100 PDNS could return both the modified answers and the original answers for malicious domain queries. So if it's stub resolver or the client select the malicious answer, the user will still be vulnerable to cyber attacks. And the second is we found 13 PDNS vendors should only protect some specific types of DNS queries. For example, it will rewrite the DNS queries to malicious domains of A or AAAA or CNAME types of queries, But if you query a TXT records towards a malicious domain, it will just return you the original answer. So the attackers, especially the malware attackers or the botnet attackers, could bypass the protection of PDNS by abusing this mechanism. We also make recommendations based on our findings for PDNS implementations. For example, to provide transparent blocking notifications to the users, and to use safe rewriting infrastructures, and to fix the security flaws we identified in this work. Okay, here's a summary of our work. Thanks for listening. Note that our code and some insensitive measurement results have been open sourced. And thanks for listening. I'm ready to take any questions.
Any questions?
Hello. Yeah. Hi. So I'm Piyush from University of Michigan. Can you provide some context as to how do you differentiate if the corrupted DNS response is due to censorship or it's due to PDNS services? Because one of the results you mentioned, you showed that you got both the forged response as well as the original response, which is very indicative of censorship of how the literature has evolved over time.
Okay.
It's very representative of censorship.
Thanks for the question. I think you are asking how do we distinguish censorship? Okay. We take several steps to distinguish censorship from PDNS services, and the first is we check the well-known censorship domain list, like the list from Citizen Lab, and we excluded those domains from our testing list. And second, we take measurements to actively measure the censorship. For example, we can see the censorship has two types of censorship. The first is from the client side. If the client located in country A and the resolver located in country B, both the censorship from country A and country B may also impact the result. So for the client side, we choose the vantage points in countries with high network freedom to mitigate the impact. And for the resolver part, we refers to existing methods, like we would query the domain to a IP address located in the country B, but the IP address provides no DNS services. But the censorship will also block these queries. So we use this method to distinguish those types of domains and exclude it out of our results. Yeah, but we acknowledge that the censorship would also, although we take such measures, it will also be some censorship to domains that be errorly, mistakenly recognized as PDNS. Yeah, it's a limitation.
Any other questions? Well, I had a question.
Okay.
Have you thought about the interaction of a DNS stack with these kind of blocking systems, and maybe implications on what blocking method will work well or not with that?
Oh, it is a great question. We do not consider the DNS stack's impact on this system, and we can do it in our future work, I think.
Sure. Okay. Thank you. Let's thank the speaker again.